to day 22 of the Data Science Challenge, where we go over machine learning model and model validation. So this course is part of the Introduction to Machine Learning course. It's on Kaggle, and I'll put the links in the chat. And this is Roja Arcuri's GitHub library that we'll go over. So it says you've built a model, and in this exercise, you're going to test how good your model is. So run the cells. So the imported pandas, they from sklearn tree, the imported decision tree regressor. This is the input file for Kaggle. There was data for Panda that was red. There was a sales price data, and there were feature columns of lot area, year built, first floor, second floor, full bath, bedroom, etc. And the X value. Model was specified. It was fit for the decision tree regressor. The first in-sample predictions were printed, and there were actual target values for homes printed as well. There's also code checking that's done. And then I guess there's some exercise here. So split your data into train, test, split to split it up. Give it the argument random state 1 and check the functions know what to expect when verifying code. So features were loaded into the data frame X and the target is loaded into Y from sklearn model selection port train split. Fill in and uncomment these values and then check. Specify and fit the model. So model was a decision tree regressor with this random state 1. Fit the IO model with train X and Y and then print out the values. Make predictions with validation data. So have a validation set. Inspect the predictions and actual values from the validation set. So that's also done. And then calculate the mean absolute value error in the validation data. And you're using sklearn metrics to import the mean absolute error. And you're calculating the value of the mean absolute error and then printing that. And they got this value. So it's pretty big. This is asking if the value is good. So there isn't a general rule for what values are good that applies across applications, but you can see how to use and improve this in the next step. So we'll go into underfitting and overfitting random forests. So now it's important to optimize the size of the tree to make better predictions. Run the cell to set up your configuration environment. So we have pandas, sklearn metrics, importing absolute error. Sklearn model selection imports train test list. Sklearn tree imports decision tree regressor. File path is there. XY data is listed. Home data is listed. Train X, validate X, train Y, validate Y. Train test split is all written. Model is listed. Decision tree regressor. Fit the model. Validation predictions are listed. Iowa model predictions. Validation mean absolute error is written as well. And then there's code checking. So binder checks the code as well. And then we have this validation mean absolute error. Here it's writing the function for get mean absolute error. And then this is using it based on the max leaf number of nodes and the training and validation sets based on our model and trying to get the max leaf nodes equal to itself. Fit the model predictions with the values and mean absolute error. You can compare different tree sizes. So you can write a loop that tries the following values for max leaf nodes from a set of possible values. Call the get and mean absolute value function on each value of maximum leaf nodes. And then store the output in some way that allows you to select the value of maximum leaf nodes that gives the most accurate model on your data. So there's candidate max leaf nodes are here. There's scores that are listed. For the leaf size, you have the best tree size, and then you have steps. And then you can move on to fitting the model using all the data. So once you know the best tree size, if you're going to deploy the model in practice, you'd make it even more accurate by using all of the data and keeping that tree size. If you don't need to hold on the validation data, you can use it for your modeling decisions. So fill in an argument to make the optimal size. An uncommon final model is decision tree regressor with max leaf nodes equal to the best tree size. Fit the final model. And then this model was tuned and the results were improved. And then we're still using decision tree models, which are not very sophisticated by modern machine learning standards, but these random forests will make your models a bit better. So we can go on to where this was actually obtained from. So this is on a Kaggle notebook. It goes over housing prices for Kaggle and gives a Melbourne housing snapshot and mobile price classification. There's a reliable way to measure model accuracy. You can experiment with alternative models and see which gives the best predictions. There's scikit-learn's documentation. The decision tree model has many options. Most important options determine the tree's depth. There is a lesson in this course. Does house have more than 2 bedrooms? Lot size larger than this? Lot size larger than that? No, yes. Those are how decision trees work. It's not uncommon for a tree to have 10 splits between the top level and leaf. As the tree gets deeper, the data sets get sliced up into leaves with fewer houses. It's talking about splits, talking about how the houses are divided in predictions. Then it talks about overfitting, where a model matches the training data almost perfectly, but does poorly in validation and other new data. Even if the tree is shallow, it doesn't divide up the houses into distinct groups. If a tree divides up houses into 2 and 4, each group still has a variety of houses. Resulting predictions may be far off for most houses, even in the training data, and it'll be bad in validation too for the same reason. When a model fails to capture important distinctions in patterns in data, it performs poorly even in the training data. That's called underfitting. So since we care about the accuracy in the new data, We estimate from our validation data and we find the sweet spot between underfitting and overfitting. And this is what we get. And there's an example for a utility function, which compares mean absolute error scores, similar to what we saw in the notebook. There's also some hidden code here, and it's giving us values. The conclusion, overfitting captures spurious patterns that won't reoccur in the future, leading to less accurate predictions. Underfitting fails to capture relevant patterns, again leading to less accurate predictions, and we use validation data, which isn't used in model training, to measure candidate models' accuracy. And then this is optimizing the model. Not really sure what this notebook has. I guess it just has a scratch pad. And this is where the course is coming from, intro to machine learning. So it talks about how models work, basic data exploration, first machine learning model, model validation, underfitting and overfitting, random forest, and then machine learning competitions. And that's pretty much it for today's video. The links will be in the description, and feel free to reach out if you have any questions. Bye for now.